So we're going to go ahead and start. Alright, so hello, we are Hornet Hyperloop. We are a team competing in the SpaceX Hyperloop competition, and we would like to be able to share with you all what we've done, what we've come up with so far, and what's going to go on, in the future. So we're looking to be able to actually run open the competition for the summer. We're actually currently within the running, and we're going to be giving a presentation to SpaceX next Friday. So it's all live right now. It's all going on pretty fast. So the overall outline, we're just going to be giving a little bit about what Hyperloop is, if none of you guys know about it. We're also going to be talking a little bit about the SpaceX competition, special loop, and then we're also going to be talking about what our design is, what the pod is, how our systems work. And so then we're also going to share some other fun stuff and see if you guys have any questions. And so here is the Hornet Hyperloop team. We're actually still growing. We need a couple more members on there. I think we got an additional 5. We're trying to be able to get as many different students as we really can. So we have electrical, we have mechanical, civil, computer science, we have some business, and a lot of other different types of major, like student majors. So that way we can actually make it a completely interdisciplinary group working on this project. And then our academic advisor is actually Lorenzo Smith, and we would like to be able to call him up over here. If he said he wanted to get a little word.
Very little word. I just wanted to take this. My name is Lorenzo Smith again, the Dean of the College of Engineering and Computer Science, and sometimes I think I have the best job in the world, and that is talk about our students. Just wanted to keep it simple and just mention that they are an example of what I'm so proud about our college. We have a wonderful set of faculty. Over the last 3 years, we will have brought in 21 new faculty members, fully accredited undergraduate programs, building new labs, but it's the students. And so hopefully tonight you'll get a snapshot of what our students are doing and get an understanding of some of the needs that they have. This is an example of excellent extracurricular activities. So I don't want to take more of your time, but I just want to express how proud I am of them. They have the support of the college, and I look forward to the presentation. Thank you.
Thank you. And then our industry advisor also wanted to be able to say a word, Captain Kurt Terrace.
Good evening. Thanks for coming tonight. As you know, the United States is at an inflection point to invest in infrastructure, invest in transportation systems, invest in our future. And the ideas you're going to see tonight are part of those. I hope you enjoy the presentation. There's a lot of excitement going on in the industry right now. There's 2 established Hyperloop companies, Hyperloop One and Arrivo, that have begun operations and R&D on this effort, in addition to SpaceX, and in addition to several teams at several universities that are preparing designs to become a component of a future Hyperloop system or become the system itself. So thank you for coming, and I enjoy to get to know you after this presentation.
Thanks, Kurt.
So my name is Dylan Craycraft. I am the Vice President of Hornet Hyperloop as well as the engineering lead. And we're going to show you a short video of what Hornet Hyperloop is and just give you a little snapshot of what our team's about. Hornet Hyperloop is a interdisciplinary team of engineers and business students. We are designing a Hyperloop pod to compete at SpaceX's Hyperloop competition at the end of the summer break.
I'm Paul Roscoe. I'm the team captain for Hornet Hyperloop. The Hyperloop competition is a scaled-down version of the full Hyperloop system, which should be able to connect cities together. For instance, San Francisco to LA in about half an hour. It would be traveling through a vacuum tube at supersonic speeds and would be employed for massive public transit systems.
My name is Mario Mercado. I am involved in Hornet Hyperloop. I am part of the structures team and currently taking on a position called transit team lead. This part development is exciting because the whole idea of the competition is to basically make a 5th mode of transportation, and you can see it everywhere. You're sitting in traffic, you want to get from point A to point B faster. It's really innovative. It's something that's never been done before, and by Sac State students being involved in that, you're being part of history.
All right, so just to kind of show you guys how fast that we work, that was actually just made this morning. Yeah, we go through and do so many things just very, very fast. We have a deadline and we meet it within a couple days whenever it's necessary. So yeah, it's just been a rush being able to actually get over there. So now we'll actually talk a little bit about what Hyperloop actually is. It's a fifth mode of transportation system. It can actually revolutionize the world. It can connect cities, like I mentioned over in the video, from San Francisco to LA. We're also looking at, as I'll mention much later on, how it can actually be fully utilized within California. Right now we're only at the initial stages, but it can also be like completely solar powered. In order to be a lot more environmentally friendly. It can be a little bit more modular, I think. Hyperloop One, another company I'll mention later, they have a good idea about that. But the main power of it is you're traveling through a vacuum that you're getting little to no aerodynamic resistance, and you are able to, by that point, travel at supersonic speeds, the speed of sound, so you can travel at 700 miles per hour or so. So, yeah. And what actually started it all off was Hyperloop Alpha. Elon Musk published this white paper over in 2013. And so the reason why he actually started coming up with this was he just got really frustrated with the traffic in LA. And it seems like that is kind of a common thing with him, because right now he's also looking at building tunnels because of that too. This is kind of a little funny thing. He's kind of obsessed with it. But yeah, it all was pretty much a preliminary outline for what he thought should be kind of a little push or nudge within the transportation system currently, to be able to just make sure that we can actually connect cities a little bit more efficiently, so you don't have to wait 3 hours to be able to get from here to San Francisco, like I had to deal with pretty often this past summer in an internship. So, like I said, this can actually connect cities. This is Hyperloop Transportation Technologies map of how they're thinking about implementing it throughout all of the United States. This is a very initial kind of thing, but you can, like I said, you can connect all over, travel like from Phoenix to Austin in about an hour, which would normally take, if you take an airline, you're going to have to wait over there for about 2 hours, travel for another hour or so, and then take a good amount more time getting out of there. And it just significantly saves time. And it is mainly used for medium level transportation, where traveling for, if it would take a car like 2 to 6 hours or possibly 12. But we'll see how it actually develops from here. And the companies that are actually building this right now, there's 3 companies that have gone public about it. There's Hyperloop One, I mentioned. They're actually contracted to be able to start doing a little test over in Abu Dhabi and Dubai. They also started the whole Hyperloop One Global Challenge to be able to further develop this. And then there's Hyperloop Transportation Technologies, like I already mentioned. They actually very, very recently got contracted, just like Hyperloop One, to be able to do another feasibility study over in Europe. And then there's Transpod. Not much is known about them, though. They're a Canadian company. They're keeping fairly private. So about the actual competition, to also kind of further develop this type of technology, SpaceX promoted this by forming a competition. So Elon Musk, the original writer of the white paper that I mentioned earlier, he's the CEO of SpaceX, and he's the main reason why it kind of got pushed forward. Also, mainly just because the public really saw this. They, were kind of sick of, just waiting over in traffic or dealing with airlines. We want to be able to have another method. So we kind of pushed for this to be able to actually go on. What we're actually doing in this competition is further developing any type of technology, as well as just proving to the public that this is even possible with current day's technology. So here's last year's pod, well, not our pod, but a little preview of what might go on. This is actually Dove Loop. Yeah, play it. Skip that. This is MIT traveling through the tube. We get up to about 80 kilometers per hour and just run. This was just a test, and you can actually see it flying right through. So the actual competition, this is more or less how the timeline is. You have to sign it up, and then you go through several stages where you might get cut or you might not. We've already passed through a couple, so we've already submitted the preliminary design, which they already passed us for, and we've already also submitted the 250-page final design report, which we'll be showing over in another room after the presentation. If any of you guys want to read it, it's pretty long, probably a little bit more, skip through the table of contents. But then this next Friday, like I also mentioned, at 3 p.m., we're going to be giving the SpaceX presentation, which is going to be pretty fun. We're going to be presenting to 2 of their engineers about our design, where we can also get past. We're actually feeling pretty good about that. They say about 40% will be able to run from there. And looking at some of the other teams, I think our design is pretty spot on. And then, of course, you have to give a safety briefing in order to be able to actually go there and test over at the test track. That's probably going to be happening early summer. And then we can actually go and fly. That's what we call it, down the actual tube itself. We're going to be doing other press release events like this. The main one is probably going to be a press release event where we reveal the actual pod itself, built and fully developed, probably right after the testing weekend. So we are not exactly sure when that will happen. Of course, that will depend upon the assembly time, but we'll let you guys know. So this is the tube that we're actually traveling through. It's a 6-foot diameter vacuum tube. So that's just steel on the outside and then a center I-beam in the middle and 2 aluminum plates on either side. So ours is set to a pressure of 0.125 psia. That's actually pretty good vacuum. Normal is 14.7 psia, and we're able to significantly reduce the aerodynamic drag, just like how it actually was supposed to be in the white paper. So another little thing, they also invited us to be able to go showcase over at the competition from last year, because last year was the first year. We also have a couple pictures for you guys to be able to view of just how it actually is at the event. So here's one of our booths right up over there. We were promised a little bit more area to be able to actually showcase some of the different things, so we had to cram it all over there. But up over here is more of the actual staging area where you can load your pod, enter the tube, and you can also view in a lot of other places. You have another example tube where Elon Musk actually sat in there, and we're hoping that he can sit in ours as well. Just a little personal goal. And there we all are over the booth. This is all the people that came there, minus Ian. He was out getting food. Yeah. And yeah, it was pretty fun. At that time, we were only able to actually showcase the preliminary design, but right now we're actually going to be showcasing our final one. And so overall, our design philosophy was focused on simplicity, safety, and efficiency. So one of the biggest factors was safety, because SpaceX is really, really strict on that. If you're not safe enough, you will not run. You won't even be able to pass. That's why they have all these little check marks. If they think that your pod is not, it might damage either their pusher or their track, they're not going to let you run. They won't even let you continue in the competition. So we placed a very high importance on that, making sure that everything completely fit according to the specs and will not fail. We placed a lot of different redundancies and try to go with passive systems to be able to reduce the potential points of failure. And then apart from that, then any type of scalability of the systems were chosen if they didn't really conflict, of course. So overall, the pod is 13 feet long and 3 3/4 feet high. Obviously, this is only meant to have one person in there. It's fairly small. It's not exactly a full system where you transport 28 people, but we can actually transport a whole person in here, as you'll see later on. And so overall, it's actually going to be 890 pounds in weight, so it's pretty light, pretty comparable to some of the other teams that we've talked to. And we actually are pretty proud of it, and we were able to significantly reduce it from what we had for the preliminary design. I believe that weighed about 1,300 pounds, quite a bit heavier, so we're trying to be able to go a little bit lighter so that we can get a little bit faster. And then this is how we're able to actually go through the tube. So we're of course going to actually accelerate. So SpaceX is providing a pusher interface to be able to get us up to speed. And then we're just going to be coasting for a little bit, and then we're going to be braking. The reason why we didn't really put an additional like propulsion system on there was mainly just for safety, and we fully expect that SpaceX would put a lot more attention in terms of whether or not it's safe enough and require a lot more time or too much time to be able to fully develop it in terms of proving to them that it's completely safe. Next year's pod will definitely have an additional propulsion system as well as an additional braking system on there. We laid out the specs for that. And so a little bit about the actual safety. Like I already mentioned, we have multiple system redundancies, so that goes into the controls as well as the actual power itself. And then we are also having several structural factors of safety. So what that really means is it can handle more forces and is stronger than what it's actually really needing to be. And then, of course, with the pusher-breaker interface, that is basically meaning that we will have a certain time period where we're being pushed and we cannot brake during that time period. And we're able to both sense that as well as have a completely physical system that will not allow that to happen. Even if all the electrical control systems or even battery systems die, it won't happen. And then we've even been able to analyze for any type of tube breach situations. So, and then I'm going to go ahead and hand it off to Joey.
All right, now we get to talk about the fun stuff, what the actual design of our pod is about. So basically the way we designed this, we designed it, we wanted to be manufacturable because most of the work we're going to be doing ourselves here at school. All the students are going to be involved hands-on building this pod, so we're going to be really proud about that. So the other thing is it has to be 100% functional, and like Paul said, it needs to be 100% safe, or they will not let us run it down at SpaceX. The other thing is, obviously, as a student organization, we need to be very cost-effective. Building something like this is very expensive, and so every little bit that we can save goes a long ways. So the systems for structure design, there's 5 different areas. There's aerodynamic design, which is the aero shell you can see up above. There's the pressure vessel, which is where the life-size dummy is seated, and as well as the interior systems that go inside the pressure vessel as well. There's the lower substructure, which is down below. It's kind of separated now. This is an exploded view. We'll talk about that a little bit more later. And then the pusher interface, which is where we engage with SpaceX's pusher. So this is just a little design right here, a little table right here that explains all the factors of safety. And what that is, SpaceX dictates that everything that we design has to be designed to a factor of safety of at least 2. And what that means is that basically the amount of forces that we're going to see from the pusher and the aerodynamic forces, we need to be able to withstand double that. So that's what that means. So this is the pressure vessel design, and it's based on a commercial aircraft fuselage. And the reason for that is, as you can imagine, in an airplane, you need to have normal atmospheric pressure on the inside, and you're in a low pressure environment on the outside. Our pressure vessel was designed with a lot of aerospace materials, a lot of aluminum. The other thing that's neat about this is it's got removable bulkheads, so we can access the inside of our pod whenever we need to, if there's something that goes wrong, or just setting things up, so we can go in there at any time. So this is just an example of the FEA. This one's for deformation. Just shows based on the amount of forces how our pod is going to deform or bend or twist. And we did this basically for every different system, verifying that it's going to be safe. So this is the interior. It's a little cross-sectional view. You can kind of see the inside. Up here, the little white thing behind the guy, that's the battery box where the batteries and battery management system is going to go. There's a racing seat, and then obviously it looks like a real person, but in this competition it's going to be a life-size dummy. And then also up in the front, on the bottom, underneath his feet is where all the controls hardware is going to go. So this is just a little example of what ANSYS software does, and basically it can mimic what our pod is going to see in the actual tube and tell us the amount of forces that we're going to feel, so we can design our pod to be able to withstand those forces. Also, another fact is that, I don't know if you guys know what a Tesla Model S is, but they pride themselves in their low drag coefficient, which is like 0.24, and our design has a lower drag coefficient than a Tesla Model S, so that's pretty cool. So this is the lower substructure, and this is a very vital part of the pod. This is where all the subsystems such as the braking and the lateral stability. If you see the wheels in the middle, that's what pinches us against the I-beam and allows us to keep going straight down the pod, or straight down the tube. There's also pneumatic braking and deployable wheels and all kinds of different systems that we'll explain to you a little bit later. This is another example of the FEA that we did for the substructure, just saying that it's basically safe and going to be all right under all the forces that we're going to be feeling. This one's pretty cool. So this right here is a picture of SpaceX's pusher. I believe this cost SpaceX almost $1 million to design, and so that's really important that they don't want any systems to mess up that or their tubes. So we've designed a little mechanism. This is the back, looking at the back of our pod right here, and this comes out the back, and the back, this little circle right here engages with the front of their pusher, and it's got a little spring. I don't know if you can see the knob coming out. That basically tells our pod control systems that we're hooked up with the pusher. And so as we start accelerating, once we get above about 25 miles an hour, we'll start hovering throughout the majority of the run. And what this spring-loaded little rod does is it allows our control system to know when we disengage and we are actually completely free-floating away from the pusher. All right, I'm going to turn it over to Ian, and he is in charge of the power team.
All right, so I'm Ian Rawl. I'm in charge of the power and transit systems. And so our power systems, the main design philosophy was to reduce the power consumption and have the fewest potential points of failure. And so the systems that this is included in is the battery systems, the pneumatic systems, the deployable wheels, the primary braking, and the levitation. And so here we have a breakdown. This is the pod's power consumption. So as you can see, the total power consumption of our pod is 300 watts. And an important point to note about this is that while we're actually running, our pod is only consuming about 84 watts. And so to put that in perspective, that's less power than that laptop is consuming right now. So we're actually consuming a very low amount of power while we're actually running. And since our pod is powered by the battery shown right here, the lower power we consume means less batteries, which means a faster pod. And so these are the batteries we're using. So we're using an array of 40 batteries. This is 8 series, 5 in parallel. This provides a 24-volt system with 2 amp hours. And we're using lithium-ion batteries. Our battery management system is a custom-built lithium system with a Zivan charger and phase change material. And this phase change material is actually really cool. What it is it's essentially almost a plastic-like material that begins to melt when heated up. So it absorbs a lot of the heat generated by the batteries. And so this is an overview of our pneumatic system. So our pneumatic system is supplied by the 2 tanks shown right here. That controls our deployable wheels, our primary brakes, and our parking brakes. So the great part about this is with the pneumatic system, it kind of makes it impervious to a power loss, which is very cool. This system is controlled by electronic valves, mechanical valves, and flow control valves. And so this is an overview of the push interface. So as Dylan showed before, we have a push interface, has a little pin, it's a spring-loaded pin. And what this does is this locks out the brakes pneumatically through a mechanical valve, so that even if we were to lose power during the pushing phase, we would not brake until the pusher let go, and to mitigate any damage done by that. This shows our primary brakes. These are eddy brakes, so it's a type of mechanical brake that uses currents, magnetic currents from the permanent magnets shown here, and that's what actually provides the braking forces of our pod. So this is no friction, purely mechanical, although we may be adding some friction brakes to this as well. And so this actually shows how the brakes work. So as you can see, while we're moving down the pod, or moving on the track, the pod's brakes are fully retracted, disengaged, and so there's no magnetism between the pod, or between the brakes and the rail. When we decide to brake, in about 1 second, these brakes move into place, and then producing a really large drag force and slowing our pod from about 207 miles an hour to a stop in about 10 seconds, 10 or 11 seconds.
This is a simulation we did, so this shows the currents produced by the brakes. This is going at 55 miles an hour, and so this shows on the top, you can see it shows the actual magnetic field as well as the intensity of the currents produced by those magnets. And so one of the things, although we don't have main propulsion for our pod, we do have a service propulsion. This is designed to take over when our pod is out of stop. So after, towards the end, once our pod breaks, most likely we're not going to be right at the end of the tube. So at that point, these motors come on, and they move our pod at about 3 miles an hour from the point we stop to the end of the pod, to the end of the tube. These are our parking brakes. So these are pneumatically actuated as well. So the idea with this is all our braking systems are pneumatically actuated to prevent from to mitigate power loss. So if we were to lose power, our pod safely stops. These parking brakes are also used if our pod is stopped. We don't have electrical power. These will hold our pod in place. And then I'm going to turn it back over to Paul to cover our levitation systems.
Right. So I was pretty heavily working on the levitation systems. So the way that we're doing it is just using 20 magnets. It's 3-inch neodymium boron magnet cubes, and they're pretty powerful. They can pretty much just kind of put a hole in your hand very easily. And they're basically just simply mounted over to the substructure. The bigger work of it is more just making it and prefabricating it off-site. That's a lot of what I'm doing. Another thing that we're doing with this one is just protecting with UHMW plastic, just a little 1/8-inch thick. That way we can make sure that nothing really comes up. Because if you remember back from the video way back when, there's a lot of rubble that can come up, and we just want to make sure that they don't really get nicked in their nickel coating, because then their magnetic properties can significantly decay. And we're also going to be doing some physical testing on this pretty soon. It's currently in development. And then we also have another little sample FEA. So this is magnetic simulation using ANSYS Maxwell. This one was for the 5 magnet long, about 1/8 inch thick in between each. And you can get quite a bit of levitation force. We're actually going to be levitating an inch high. It's pretty high, especially relative to some of the other teams where they're only going for about half an inch or so. We want to be able to make sure that there's no larger track deviations than what might have been in the actual tube itself, as compared to what is currently on the specs. We just kind of, love a little safety thing, going a little bit above and beyond. So I'm going to go ahead and hand it off over to Prem for controls.
Hi, my name is Prem. I'm the controls lead of Hornet Hyperloop. Controls was basically developed to automate every phase of the pod it's going to go through its journey. So it's going to comprise of a ground control station, software, and hardware, and along the sensors. So what you see right here is the user interface, or the overview of what the person will be at the base station looking at. These are the key vitals that are coming out from the pod. For example, like position, levitation, and various mechanical systems, whether they're being engaged or disengaged. What we see in this particular picture is when the pod is in pre-flight. This is the point where the pod is in the staging area inside the tube and waiting for the pressure to drop from 14.7 psi, that's atmospheric pressure, to about 0.125 psi. And so at this point we have the push interface is engaged. As you can see, it's in green, and then the braking is disengaged, the wheels are deployed, and the pod is completely ready for its acceleration state. This is the software. The software is more responsible for monitoring the data coming from the microprocessors and updating the base station. It flows through a cyclic process of 4 states, starting from idle, acceleration, coasting, and braking. The pod spends most of its time in idle, and when we detect the push interface, it will move to acceleration phase and wait for SpaceX to give you the initial push for 1,500 feet. After that, the pod will go into coasting, which is where it reads from every sensor for about every 10 milliseconds, and that's enough data points to cover and pass it to the base station. A simple math, if we try to do a mile traveling at 200 miles, it takes you about 17 seconds. So we want to make sure that we can break those 17 seconds into enough data points and assure SpaceX that we have enough data and we're safely navigating the pod throughout its journey. To host the software, we have hardware built into it, and hardware is completely redundant. As you can see, the solid lines clearly show that they're the active systems, and the dotted lines are inactive. What they mean is they will be receiving inputs from all the sensors, but they will not produce any outputs. In any case of fault or any case of a hardware malfunction, the inactive system will take over, and the base station will not even know that there has been a malfunction, and the pod will still be able to navigate itself. This is where the controls are located within the pod. It's on the wooden frame, and on the right side you see the two RPIs, which will be hosting the control software, and the microprocessors are ARM Cortex-M3. They will be reading from all the sensors at 10 milliseconds rate. These are the location of various sensors on the pod. We have 18 sensors in total. The major ones are proximity sensors pointing down and retroreflectors pointing up. Retroreflectors are used to figure out the position. A mile broken down into feet is 5,280, so we have retroreflector tape on the tube every 100 feet. Going down the tube, we'll be able to track those tape and figure out what a position is. And proximity sensors pointing down to figure out a levitation height. And back to Paul.
So I just kind of want to also mention a little bit about the tube breach. This is kind of a little sample FEA where, just another little example of some situation that we took. What if the actual tube itself breached? So we have a significant impact of, the actual airflow is coming in at regular pressure and it completely pushes past our pod. What about if all of our different systems on the substructure, they might get blown off or damaged by that significant, sound wave. So we've been able to actually protect it with that aero shell as well. That's one of the other functions of it. And it's completely safe enough with a whole factor of safety of 2.5. So it's totally fine. And so I just wanted to tell you about some of the other fun stuff that we're doing. Like I mentioned before, we're doing a tube side project to be able to see how it would actually be employed within all of California. So which stops that it would be, how the tubes would be laid out, what kind of connections that would be, so how it would connect with the Y in terms of any types of branching, and all of those different types of things. And then of course some of the vacuum, VR, wind tunnels, and other Hyperloop development kits. So this is the one that we have right now. Right now we're actually looking at having it completely going all the way through, so it's not really stopping at any of these unless the actual system wants you to. That way you can actually have a Y component right over here, come off, go to the base station, go off. That way you can have smaller and more modular pods being able to actually travel through there. Mainly because when you're traveling at the speed of sound, it takes a long time to go slow down and speed back up. And because a lot of the different people, they want to be able to go from A to C without going, hitting past B. And then we're also looking at keeping it along a more or less even elevation. Some of the other parts, we're looking at where to be able to tunnel, more or less how would we tunnel. We're leaving that one more for Elon because he's working very heavily on that one right now. And we got a couple different places right now that we're looking at, more like Sacramento, East, South Bay, down over to LA, San Jose, and a couple other places. So yeah, we can talk about that more over in the room that we're going to be hanging out afterwards, if any of you guys want to talk. Some of the other stuff we're doing is virtual reality. I believe we should... Okay, they're there in the room? Okay, so we might be able to show you guys some of that today. It's more just a simple little export from SolidWorks, our 3D modeling system, and then uploading, or a little bit of processing, and then uploading them to the virtual reality system to be able to better visualize the systems. We're also developing some augmented reality that we're also having over there. And then this is a little bit about the wind tunnel. So we were able to actually do some physical testing. Right now it is inoperable. Apparently there was a little bit of a problem that came on. Totally not our fault. We checked. Yeah, but anyways, we were able to actually do it with version 1. We're going to have the 3D printed model out there as well. We have a newer 3D printed model. We weren't able to do physical testing for that one, however, as it broke right around when we were printing it out. But this was actually done right over here at Sac State, so we have our own wind tunnel that we can actually test it at. And it's actually pretty fun. I like it. You'll actually be able to see video. right over here. This one was the version 1 that we did. Also, the smoke machine wasn't all too powerful, so a little bit of it. So. That was the first one, obviously. Well, and then here's our Hyperloop development kit. This is kind of a little small test bench that we made to be able to, just kind of prove some of the whole high-rack array. Most of the engines and the actual magnets that were mounted were bought. And we actually have this over there. We're going to be able to see it run. We're also going to be using it for some controls test bench. That way we can have a custom filter on some of the IMUs and some of the other sensors, because those sometimes behave a little bit differently whenever they're in a vibrating environment, which due to some of the vibrations caused by the levitation and the braking system it will have. So overall, the pod cost is going to be about $55,000. Everything else, that's actually for the total project. The pod materials cost is expected to be about $35,000. We're expecting for any type of overall testing apparatuses that we're going to have to do for SpaceX. That will of course fluctuate because, like I mentioned, they say, hey, by the way, test for this. At least that's what we've heard. Just kind of totally off the bat, get this done within 2 weeks. But yeah, we're just kind of allowing for a little bit of leeway within there, just kind of expecting them to do that. And then, if any of you guys want to be able to help out, we're looking for funding, of course, but even if you're a student, if you want to be able to help out, even if you're not an engineer, we're looking for that, be able to do some separate side studies. We want to be able to grow this to be as interdisciplinary as possible. You can help out with the media, event setup, or anything else. And then, of course, if you're a parent or if you really just work in general, you can help talk to your companies and maybe get them to help sponsor us, even if it's giving us free food for all those late nights or possibly some materials or, a little bit of monetary donations. So we got little examples, And then we also have some T-shirts that any of you guys can actually buy. We just finished making these. We have, just some regular T-shirts, some hoodies, and all that. We have some laptops set up over in the room right across the hall where you guys can actually buy these. I think they look pretty awesome. I think even a little bit better. Yeah, they're relatively cheap. So, we also just kind of wanted to thank our sponsors. Actually, one of our sponsors is right over here, Precision Belter Group. Raise your hand. Yeah, so far we only have 5, but my guess is they'll probably grow to 25 pretty soon. I know there's a couple companies that we're already talking to right about now from the other teams that we talked to. Right when you actually submit the final design report and give the presentation, things start exploding. We've noticed that. So anyways, so does anyone have any questions? No?
You guys mentioned that some of what it will be built out of, will it be carbon fiber?
There may be carbon fiber depending upon whether or not we can get that donated. That would probably be used on the nose cone. Right now we're looking at using A-glass because it's a little bit cheaper and more available. We're trying to be able to talk to several companies in order to be able to maybe make that out of carbon fiber and make it a little bit lighter.
A couple people mentioned around a 200 mile per hour speed in the test track. Is that based on your belief that you're going to go 200 miles per hour, or is that theoretical?
That one is a little bit theoretical. It's based on how fast that SpaceX actually pushes us. What we saw in last year is they're very picky in terms of accelerating you to a certain degree. They only do it how safe they really feel that you are. They apparently do it they accelerate you at quarter G and then half G and then 1G. That one was for the 1G that they specified over the track specs, but it's kind of up to them as to how fast that they push us because we're getting all our propulsion from that. In later years, like I mentioned, we're going to be having some electromagnetic propulsion, probably using lithium or an LAM to be able to actually assist in that, and hopefully we can go a little bit faster than what they say or do. So of course we're going to be abiding by all their safety specs, but Yeah. Here, Dylan wants to say something.
So if you, as you notice in the video of the two and the last one, the MIT team, the reason that they ended up only going like 80 or 90 kilometers an hour was because at last year's competition, being the first competition, SpaceX's pusher had quite a bit of issues. I remember specifically talking to a few teams, and that was a big issue they were having with because they had done all their magnetic analysis and all their analysis based on, what SpaceX had assumed that they were going to be able to provide, and they actually were not able to provide that exact acceleration profile. And so it was kind of an issue. So I think in this next competition, they're going to have it dialed in a little bit better and be able to provide a more constant acceleration. So.
Yeah, the whole whether or not it's safe enough is both for their pusher and the pod. So, yeah, anyone else?
Does the individual in the pod experience the G-forces both on the acceleration and deceleration?
Yes, but it will be a dummy. So, yeah.
But I mean, eventually, I guess the next question would be, when a human becomes the occupant, is the human going to experience those G-forces both on the acceleration and deceleration? If it's going to go up past 1 G or
Yeah, so that would be more for full scale. At that point, it would definitely not be accelerating quite so high. My guess is it would max out at maybe 1/8 of a G, at least for some applications. That is, of course, dependent upon the actual company itself. With the actual tube study, we're going to be looking at more human comfort levels and what would actually be acceptable for that. That way we can more accurately estimate any type of time differences between locations. For ours is purely more for just kind of proof of concept because we're only given a certain length of track, so we're trying to be able to go as fast as possible, but within the actual full system you're going to utilize a lot longer to be able to accelerate slower while still getting up to the speed that you want. Does that answer your question? Okay.
So I feel like if you're an accelerator from going an airline, but if you don't accelerate that much, what is the minimum distance that this would be like a good use of the Hyperloop? Like to be able to account for the acceleration and the deceleration, like would it be 100 miles or 200 miles?
So one of the most talked about cases is from San Francisco to LA, and you can actually provide more points, like how we showed on the point before. But that's only if you don't really stop by them. That's only if it's optional to be able to stop by them. That way you don't actually have to take all that time to be able to accelerate and decelerate, like I was talking about before. But you can possibly use it from here to San Francisco. You would have to probably travel at a much slower speed because you wouldn't exactly have as much distance to be able to actually accelerate that high. But it's entirely dependent upon the different systems. It would most likely include quite a bit of different places. They might provide the ability to be able to go a little bit shorter distance. So for example, here in San Francisco, my guess is they would because there's, what did you say about?
30,000 people that commute daily from.
So on a daily basis, there's about 30,000 people that commute from Sacramento to San Francisco for work. So as you can imagine, that's if we could capture even a third of that, you'd have quite a bit of back and forth transportation. And the other thing too is. I think, what did you say, 1/8 of a G would be for the human comfort, and so it's you could withstand more than that. I mean, in an airplane, you're experiencing a lot more than 1/8 of a G. Yeah, so I don't think it would take quite as long as what you guys are thinking to get up to speed. But yeah, it's definitely doable, and it would be beneficial for everybody. So.
Does that answer your question?
Yeah.
Okay. Yeah. If you want to a general sense, it's like if you take longer than 2 to 3 hours to be able to drive there, it can definitely shave off probably over an hour, or it would probably be able to travel through there in about 10 to 15 minutes. So that can significantly reduce your headaches within traffic. It would have for me. Anyone else? All right, so over in another room right across the hall, it's called the lobby suite. We're going to be doing a little bit more meet and greet. So if you want to ask a little bit more specific questions to some of the different team members, we got a few up here. We also got others in the audience. They're all kind of wearing black shirts except for this one right up here. Yeah. So, and then we're also going to show that Hyperloop development kit and some of the other different things, as well as the final design report, the preliminary submission that we put before, as well as even the original letter of intent. So, everyone, slowly move on over there. We'll see you over there.
What's that? Oh, yeah.
You got him.
Sure, so you can just say, oh, that was mine. Like, the 55 bucks they got from the garden,
And what was the grocery bill when you got out of there?
well, that doesn't count, just because I went in and shopped myself.
Yeah, all I have to say, Ian, is, oh, that's what that is. Yeah.
See, I thought it would be nice.
That's the murder of the assassin. That's it, yeah.
I thought it would be nice if somebody else was like me and had more of an explanation. When I then tried